Hello there, Mr. Sutton here, bringing you the AB Calculus 611 Extra Practice number 3 solutions on accumulation and rate in, rate out free response practice. For this calculator-based free response, let's look at the backstory here. Looks like there's a whole lot of stuff going on. So this figure here is an above-ground swimming pool in the shape of a cylinder. We have a radius of 12 feet, height of 4, and this pool contains 1,000 cubic feet of water at time 0. During the interval from 0 to 12 hours, water is pumped in at a rate of P of t. They're not telling us what the P of t function looks like algebraically. However, they gave us a table of values of P of t up here. So that might come in handy. Now, during the same time interval, water is leaking from the pool at a rate R of t that is actually given right here. And just for good measure, they told us that the volume of a cylinder is pi r squared h. Okay. So our first task on this problem, we need to use, let's see here, use a Riemann sum, midpoint Riemann sum, with 3 subintervals of equal length to approximate the amount of water pumped in the pool between 0 and 12 hours. So basically, P of t, that's our rate at which the water is being pumped in, but we're going to try to approximate how much water was pumped in between 0 and 12 hours. So we're going to say that the integral from 0 to 12 of P of t dt is approximately equal to the following. And notice I wrote approximately, not equals, because this is very much just an estimate. Truth in advertising. If you put equals here, you probably won't get credit on the AP test. So we're going to have a midpoint Riemann sum. That's going to be 3 rectangle areas that we're adding together. So we have the base of the rectangles times the height. For the base, we're just using the interval length. Now, they said they wanted us to use, let's see here, 3 subintervals of equal length. So if I'm going from 0 to 12, splitting that into 3 pieces, each subinterval must have a length of 4. So my first rectangle is a rectangle that goes from 0 to 4. I've got a base of 4, that's just the time difference there, times a height of, now for the height, we have a middle, we have a left, a middle, and a right height for each of these rectangles. Because this is a midpoint Riemann sum, we're using the middle height. So I have a base of 4 times this middle height of 46. For the next rectangle, I have a base of 4. It should be the same base for all of these, times a height of 57, because that's the middle height value there. Then for the last rectangle, we have a base of 4 again, times that middle height of 62. You don't have to simplify this. You could just put the units on the end, which in this case, this is the amount of water that gets pumped in. So this is going to be cubic feet of water. But I am going to go ahead and simplify it because, I mean, it's a calculator problem, so why not? To save a little bit of time on the calculator, since these all are being multiplied by 4, I'm just going to factor out that 4 and do 46 plus 57 plus 62 inside of parentheses, giving me a grand total of, that's going to be 660 cubic feet of water. For this part of the problem, we want to calculate the amount of water that leaked out of the pool during the interval from 0 to 12 hours. Well, we have a rate of change for leaking. That's this R of t that they gave us here. So we just need to take the integral of R of t to find the total amount that leaked out. This is going to be the integral from 0 to 12 of R of t dt. And they already defined R of t, so I don't have to rewrite all that stuff. I do need to do this on the calculator, though. So I'm going to start by actually putting my R of t function in y1 and my y equals. I have a feeling I might need to use it again. Let me quit out of there now. And I'm going to do math 9 to get integral. So we have integral from 0 to 12 of, let me do alpha trace, and then y1. That's where I stored R of t just now. Let me put a dx over there and press enter. So that gives us 225.594, and that is also cubic feet of water. For this part, they want us to use the results from parts A and B to approximate volume of water at time 12, round it to the nearest cubic foot. So there's 3 things that go into this. First, you can't forget that we had some water in the pool to begin with. We started with 1,000 cubic feet. So I'm going to start by having that 1,000 written down right away. And to that, I need to add the integral from 0 to 12 of P of t dt. That was the amount that got pumped in from time 0 to time 12. And from all this, I need to subtract the integral from 0 to 12 of r of t dt. That was what I did in part B. So this is going to be 1,000 plus, let's see, in part A, just going back to part A, we had 660. That was the amount that got pumped in. So we have 1,000 plus 660. And in part B, if I just go back to that real quick, we had 225.594. That was the amount that got pumped out. So let's go ahead and subtract 225.594. Let me do all of this on the calculator now. So crunching the numbers on there, if I round that off to the nearest cubic foot, that comes out to 1,434 cubic feet. And now it's time for the final boss battle on this free response. Part D, we want to find the rate at which the volume of the water is increasing at time equals 8 hours. Well, they're telling us that the rate is increasing to begin with, so we should at least end up with a positive number. Now, to figure this out, we need to take the rate at which the water is being pumped in and subtract the rate at which the water is leaking. So basically, we need P of 8 minus R of 8. Since P of 8 is actually defined up in this table, it's 60. We don't have to explicitly write that. It's up there. And R of 8, here's the R function. We can just plug 8 into that on the calculator. So let's see what that comes out to. Here's what that looks like on my calculator. P of 8 from the table was 60. And I stored the R function as y1 and my y equals on the calculator. So I did alpha trace y1, and then I plugged 8 into that. And that all comes out to about 43.242. Now that's going to be, since this is the rate at which the volume is changing, this is going to be cubic feet per hour, just like the units of P and R. And while I'm at it, I'm also going to store this. I'm going to store this as a variable, or actually a constant on my calculator. I'm going to store this as A, because I have a feeling I'm going to need this number again. Just if you read ahead on the problem, you'll see that you will need this again. So a whole bunch of things happened here. I stored that as A. I'm going to refer to it as A in my work. There was the actual number. There was our units, cubic feet per hour. And now we move on to the next part of the problem, which is to ask, how fast is the water level in the pool rising at time 8? So we're asking for essentially the rate of change of the height of the water, which is the water itself is in the shape of a cylinder, and we already have the rate at which the volume is changing. So this is going to end up being a related rates problem. We have this formula here, V equals pi r squared h, that ties all the quantities together. And with related rates problems, we typically take that tie it together formula and take the derivative of everything with respect to time. However, before we do that on this one, we want to get rid of this r because, I mean, right now we have 1, 2, 3 different variables, and that's going to be a pain to deal with. The good news is that the radius of the water is going to conform to the radius of the pool in general, so it's always going to be this constant radius of 12. So when I'm writing out my volume formula, I can actually write volume equals pi times 12 squared times h, which is going to be 144 pi h. And now I can take the derivative of this thing with respect to time. So derivative of volume, that's going to be dv over dt. And derivative of 144 pi h is just going to be 144 pi dh over dt. So we have dv over dt and 144 pi dh over dt. Now again, we know what this dv over dt is. We just found the rate at which the volume is changing at 8 hours. That was the first part of this problem. That's that quantity A that we talked about earlier. We're looking for dh over dt. So I'm just going to plug in A for dv over dt, like so. And now if I divide both sides by 144 pi, that'll give me dh over dt. So let me go ahead and do that on the calculator. Now, you do have to be a little bit careful when you do this on the calculator. If you're dividing by 144 and pi at the same time, you need a parentheses around those if you're just using the regular division button, or you can do what I did here and use the fancy fraction, so the calculator takes care of the PEMDAS for you in that situation. So this is going to end up being 0.096, and dh dt, that's the rate at which the height of the water is changing, so that's going to be feet per hour. So there we go. So, what's more fun than a few thousand bees? How about a free response problem on a few thousand bees? Specifically, we have a hive containing 3,500 bees at time 0, and during the interval from 0 to 4 hours, bees are entering this hive at a rate modeled by this E of t function, measured in hundreds of bees per hour. During the same time interval, we're leaving at a rate modeled by this L of t function, also measured in hundreds of bees per hour. The first task on this problem is to figure out how many bees leave the hive during the interval from 0 to 2. So we have the rate at which bees are leaving, that's this L of t function. So we need to integrate this L of t function on the interval from 0 to 2. So I have integral from 0 to 2 of L of t. Now, because this is a no calculator question, I'm going to have to do this by hand and use the fundamental theorem of calculus. So let me take my antiderivative. Using my reverse power rule, that's going to be bumping my my exponent up to a 2. Dividing by that, I've got negative t squared, and then plus 15t, all of that evaluated from 0 to 2. So I've got all of this stuff with 2 plugged in, minus all of this stuff with 0 plugged in. So the good news is that the stuff in this second bracket is all gone because everything's getting multiplied by 0. Over here in the left bracket, this is going to be, careful with your PEMDAS here, this is negative 4 plus 30, which comes out to 26. And don't forget the units. We just figured out how many bees left. So this is going to be 2,600 bees leaving. On this part, they want an expression with one or more integrals for the total number of bees in hundreds in the hive at time t, given the time interval from 0 to 4. And then they want the total number of bees at specifically time 4. So first off, our total number of bees in general, which I'm going to call B of t, that's going to be my starting amount of bees, which was 3,500 bees, plus now we have to have an integral from 0 to whatever time you're looking for. So we'll say from 0 to t, integral from 0 to t of, and now I have to integrate the rate at which the bees are changing. So this is made up of 2 parts. We have the rate at which bees are coming in and the rate at which bees are going out. To find the overall rate of change for the number of bees, we need to do E of t minus L of t, rate in minus rate out. But I can't write t inside the integral because I've already used t here in the upper limit of integration. So instead, I'm going to write E of x minus L of x dx. And this is a formula that I can now use for total number of bees in the hive. I'm going to use this now for finding the total number at time 4. So B of 4 is going to be my initial amount of 35 plus the integral from 0 to 4 of, well, now I have to do a little bit more. I mean, this was good enough up here for just writing a general formula because E and L, they're both defined and everything is, clearly defined what it is. But to actually do this without a calculator, I'm going to have to do a little bit of algebra, simplify this, take an antiderivative or two. We've got some work to do here. So E of x minus L of x. Let's see what's going on with that. So I've got my E of x function, which I'm actually going to go back to using t's in here. It doesn't really matter because I'm not explicitly writing t in the limit of integration anymore, and it's just a dummy variable, so as long as I'm consistent. So in here, I've got E of t, which is going to be negative 3t squared, and there's nothing to cancel out or combine with that with the L of t function. And now I have a 16t, but I'm subtracting L of t, which already had a negative 2t in it. So I really have 16t minus negative 2t, so that's actually plus 18t. And then there's no constants in the E of t function, but L of t has a 15, and again we're subtracting L of t, so that's going to be minus 15, and I'll stick a dt in there for good measure. Let's take our antiderivative now. So this is going to be bumping up to a 3 for the exponent. Dividing by that, I have negative t cubed, and I still have that 35 out in front. So negative t cubed plus, this bumps up to a 2 for the exponent. Dividing, we have 9t squared. And then finally, this is going to be minus 15t, all evaluated from 0 to 4. So that's 35 plus all of this stuff with 4 plugged in minus all of this stuff with 0 plugged in. Now all of this stuff with 0 plugged in is just going to be 0, so that's nice. We still have to do some number crunching over here. I mean, actually, it's all constants, so you could just write b's at the end of this, and since it's all constants, you would be done. But if you wanted to simplify it, we have 35 minus 64 plus, let's see here, this is 9 times 16, which is 144, I believe. And then we're subtracting 60. So what do we have going on here? We have a positive 35 and 144. That's 179. And we're subtracting 124 from that. So that comes out to 5,500 bees. For the last part of this problem, they want us to find the minimum number of bees in the hive between times 0 and 4. So to find the minimum number, we need to use the candidates test on this one. We're going to try out the number of bees at 0 and 4, the two endpoints, and also we have to test out any critical values in there. So let me start with finding critical values. So we need B prime, the rate of change of bees, equal to 0. Now B prime is really just E of t minus L of t, rate in minus rate out. So we want to know when that equals 0. And recall from before that this, if you combine these two expressions here, this was just negative 3t squared plus 18t minus 15. So we want to know when that all equals 0. I can factor out a negative 3, leaving me with t squared minus 6t plus 5 equals 0. And two things that multiply to 5 and add up to negative 6. That's going to be t minus 1 and t minus 5. So we see we have critical values at t equals 1 and 5. Now 1 is on the interval from 0 to 4, so we're going to have to test that out. Luckily though, 5 is not on the interval, so we don't even have to look at 5. So now let's plug in our three numbers, 0, 1, and 4. Those are our three candidates. So for 0, this one's actually not so bad, and again, b of t is the number of bees in the hive. So b of 0, well, that's just what they told us here. We had 3,500 bees at time 0. So that's just 35. We basically get that one for free. Next, I'm going to find b of 1. That's going to be the 35 I started with, plus, using my formula from before, I have the integral from 0 to 1 of e of t minus L of t dt. And let me put another parentheses in there. Now, just to refer back to what we did in part B, when we took the antiderivative of e of t minus L of t, which is this expression over here, that was negative 3t, or negative t cubed plus 9t squared minus 15t, and I'll just write a plus c because this is an indefinite integral I'm showing you here. So we're going to have 35 plus all this stuff evaluated from 0 to 1. So I've got all this stuff with 1 plugged in. That's what's getting added to 35. Minus all this stuff with 0 plugged in, which is actually just going to come out to 0 over there. So whatever this comes out to, this is my number of bees at time 1. Now I do need to simplify this because I'm trying to compare these with the candidates test. I need to know if this comes out to a number that's more or less than 35. So let's see here. In here we've got negative 1 plus 9 is 8 minus 15 is negative 7. So 35 minus 7 comes out to 28. So we have 2,800 bees after, let's see, that was after 1 hour. And finally, we have b of 4. We have to test the other endpoint there. Now, the lucky part about this is we actually found this back in part B. No pun intended. That was 5,500 bees. So now looking at all these, we wanted the minimum number of bees. That was, we have a choice between 35, 28, and 55. So that comes out to 2,800 bees. For this free response problem, we have a 12,000 liter tank of water filled to capacity. At time 0, our water begins to drain out of the tank at a rate modeled by this R of t piecewise function here, which is in liters per hour. And we want to know for the first part of this problem, is R continuous at time 5? Well, to establish continuity, we have to, especially at a border value here, we have to look at the left and the right limit and also the function value at time 5. So for the limit as t approaches 5 from the left side of R of t, we're basically plugging 5 into this less than 5 function right here. So we have 600 times 5 over 5 plus 3. So that's going to be, let's see here, 30,000 over 8. And I'm going to go ahead and simplify that on the calculator just so I can compare it more easily to the right side limit. So this comes out to 375. And by the way, this also happens to equal r of 5 itself, the function value, because this was t less than or equal to 5. So we're going to need that if we're going to try to prove that this thing is continuous. Now we also have to take a look at the right side limit. So limit as t approaches 5 from the right side. We're plugging 5 into this second rule here, this greater than 5 rule. So that's 1,000 times e to the negative, let's see, 0.2 times 5. This is really negative 1/5 times 5. So this is really e to the negative 1. And all of this then is going to come out to 1,000 over e. Well, e is an irrational number. So I don't know what 1,000 divided by e is, but it's not 375. In fact, if we look at our calculator, just do this division here. This comes out, I mean, it's not that far off, 367 and some change, but it's not exactly the same thing. So we see here that these limits do not match. So the limit as t approaches 5 in general does not exist. Because the limit does not exist, that means our function is not continuous at t equals 5. For this problem, we want to know the average rate at which water is draining from our tank between times 0 and 8. So since r is the draining rate function, we basically are trying to find the average value of the r function over the interval 0 to 8. In order to do this, I need to do 1 over the interval length. So that's going to be 1 over 8 minus 0 times the integral of r from 0 to 8. There's just one problem with doing that. R is not the same function all the way from 0 to 8. About t equals 5, we're switching from one function to a completely different function. And we've already shown this is not a continuous function, so we shouldn't assume that we can use just one rule to integrate this entire thing. But that's all right. We're just going to split this up into two different integrals. So I'm going to have the integral from 0 to 5 of 600t over t plus 3 with a dt there. And then we're going to add to that the integral from 5 to 8 of 1000 e to the negative 0.2t dt. So all of that we're just going to do on the calculator now. To make my life a little less unwieldy, I'm going to put those two different rules from 0 to 5 and from 5 to 8 in my calculator y equals as y1 and y2. And now let me quit out of there. And I'm going to do, let's see, fancy fraction mode, n over d, so 1 over 8 times, and now I'm going to do parentheses, math 9 to get my integral. We're going from 0 to 5. And in this first integral, I'm going to put y1, so alpha trace y1. That's where I stored the 0 to 5 version of r of t. Don't forget the dx. And now let's add another integral. So math 9 again, from 5 to 8. This time I'm doing alpha trace y2, because that's where I stored the 5 to 8 version of r of t. And we'll put a dx there and close my parentheses for a grand total of average value of 258.053. And since the original unit was, let's see here, this was liters per hour, this is also going to be 258.053 liters per hour. For this part, they want us to find r prime of 3 and then explain the meaning of that value in the context of the problem. So to take the derivative of r at 3, well, I need to take the derivative of this first rule here and plug 3 into that. Now, I don't actually need to calculate or look algebraically at what this derivative looks like. I could take the derivative analytically, and that would be a nice little quotient rule to plug things into. But rather than doing that, I'm just going to let my calculator do that work. What I am going to do is I'm going to show that I'm taking the derivative of this rule specifically on my calculator. And I can show that as follows. So I'll write r prime of 3 equals d over dt parentheses, and now I'm just going to put this whole first rule in there, evaluated at 3. So that just tells people, hey, I'm taking the derivative of this specifically at t equals 3. And now let me do that on the calculator. So just to review what I did in part B, I actually entered this first rule conveniently as y1 in my y equals. So quitting out of there, I am now just going to do math 8 and take the derivative, so dx, take the derivative of y1, so alpha trace y1, at the x value 3, And that's going to do pretty much what I wrote down here. So press enter. Comes out to, well, if we round to 3 decimals, that's 50. And now what are the units going to be? Well, if I'm taking the derivative of liters per hour with respect to time, that's dividing by another hour unit. So this is going to be liters per hour squared. And what does this mean? This means that at 3, what's the time unit? 3 hours. At 3 hours, the drainage rate, R of t, is increasing at a rate of 50 liters per hour squared. For this last part of the problem, they want us to write but not solve an equation involving an integral to find time A, and that's the time when the amount of water in the tank is 9,000 liters. So if we're talking about getting the water down to 9,000 liters, our equation is going to have the general format of the amount of water we're starting with minus the amount of water that drains out, equaling this 9,000. So we've got 12,000, that was our starting amount of water. Now, how do we describe the amount of water that leaked out? Because that's really the only thing that's changing here is the amount of water leaking out. Well, we have a function for the rate at which water is leaking out, R of t. We know that when we take the integral of this over some time period, it gives us the amount of water that leaked out. So specifically, we want to know how much water is leaking out from time 0 to time A. This is the magical time when enough water has leaked out that 9,000 liters is left. So I'm going to write minus the integral from 0 to A of R of t dt. So this is subtracting all that water that leaked out. And again, if I take away all that water, I should only have left the 9,000 that they said in this problem. So here's our equation that we can now use to solve for this A value.